All right, so here's a little bit of a lesson on dependent or paired t-tests. And let's take a look. So let's say that I wanted to do a study and I wanted to find out whether students do better before or after they take a nap. So this is saying they could do better before or after. That makes it a two-tailed test. So I give a sample of 100 students a test, and they score 50 on it, and then they take a nap, and I give them another test, and they score 53 on this other test, and I want to see whether that difference before and after the nap is significant. So the null hypothesis is that there's going to be no difference between the population means. And in this case, where you got one sample that you measure twice, the question is whether they represent a different population before they take the nap and after they take the nap. So they would be, although it's a single sample, they could be representing a pre-nap population and a post-nap population. Or if there's no difference between these means, if it turns out to not be statistically significant, then you just say, all right, it's just basically the same population because there's no difference between them. And because it's a two-tailed test, the alternative hypothesis is here that the pre-nap and post-nap means will be not be equal. They'll be different. I'm going to do an alpha level of 0.01 for this test, and then the degrees of freedom is going to be the number of scores minus 1, which would be 99. And in Appendix B, we'll probably use a 60 degrees of freedom because that's the closest to our actual degrees of freedom, but below it. And that number is 2.660, but 99 is a little bit closer to 120 than it is to 60, so we'll look up this one too and see if our observed t-test is going to be significant with either one of these critical t-tests. Remember, critical is the t-value you look up in the chart. So, I gave you the standard deviation of the difference between the means, which was 10, right there. And to turn the standard deviation of the difference between the means into a standard error, you got to divide that standard deviation by the square root of the sample size. Square root of 100 is 10. 10 divided by 10 equals 1. So this is our standard error of the difference between the means. Remember, I will give you the standard deviation of the difference between the means for paired t-tests. You then have to convert that into a standard error. And then our t-value, right here, our t observed is going to be the pre-nap mean minus the post-nap mean over the standard error of the difference between the means, and we get a value of -3. So -3. All right, so our t critical, remember from the previous page, is plus or minus 2.660. That's because it's a two-tailed test, and our t observed is -3. This means our observed t-value is going to exceed our critical t-value. And by exceed, I mean further along the line, further down the distribution. So let's take a look at that real quick. Okay, so with the two-tailed test, we have two critical t-values, one on the positive side and one on the negative side there. And our observed t-value falls over here, and that is in the region of rejection because it is further negative than our critical t-value. So then we just have to wrap words around our results. Our observed t-value exceeded our critical t-value, therefore our results are statistically significant. The difference between the sample means did not occur by chance, and we conclude that students do better on tests after they've taken a nap than before they take a nap. on average in the population. So remember, when you're wrapping words around t-tests, you always need to talk about populations and you always need to talk about means. So another way of saying it would be the population mean of students after they take a nap is higher than it is the population mean of students before they take a nap on some test. That's it for dependent samples t-tests.